Good morning and welcome to today's webinar, How to Design Functionally Safe Automotive SoCs from the Processor Level. Today's speaker is Rich Collins, Senior Product Marketing Manager for ARC Processors and Subsystems at Synopsys. Rich has over 25 years of experience in embedded semiconductor R&D, product marketing, and business development. Rich, please take it away.
Excellent. Thank you, Toby. So today we're going to focus a little bit on some trends around the automotive space, in particular, autonomous vehicles, and look a little bit as an example, an ADAS example, and then safety related around that, and then kind of move towards some of the architectures that we're seeing in the market and some of the product offerings that Synopsys has to address some of the challenges in the space. So the industry has done quite a bit of analysis of accidents that have caused fatalities around the world, and tried to do some analysis of what were the cause factors for those types of accidents. And you can see that they're broken down into some categories. Basically, the largest two being mental factors, incorrect decisions, and then moving toward unexpected behavior. And technology being kind of the lowest, the smallest, where there's an actual failure in a vehicle. And so what that sort of boils down to is that people are inherently bad drivers. So the best way to sort of reduce the overall impact of fatal accidents is effectively to reduce the decisions that the humans, who are the weak link in the system, can make. So if we look at the roadmap to automation, the industry considers 5 different, technically 6 levels, but from level 0 to level 5, moving toward from driver only, no systems, no assistance whatsoever, all the way up to full driverless systems at level 5. And you can see that the stages, moving toward different levels of assistance to the driver as you move up the different levels. Today, we're largely here between level 2 and level 3. Obviously, different vehicles have different levels of assistance in the car, but a lot of the features that you see are pretty common in a lot of vehicles that you buy, especially if you buy new vehicles today. Things like lane assist, where if you fall asleep and your car tends to drive out of the lane, the vehicle could either alert you, which is more of the level 2, or it can actually take some sort of corrective action and keep the car within the lane, which is starting to move toward level 3 and even toward level 4. You see these kinds of features, like I said, are pretty common in most vehicles, or a lot of the newer vehicles in the market today. From an architectural perspective, there are a lot of the automotive vendors are starting to look at building systems that are sort of connected. So whether it's the powertrain system driving the vehicle, or if it's the driver assist features, or the comfort features, and then the infotainment is an important part of that as well. Those are kind of the major areas that architecturally the car is being structured around. And more commonly, we see a connected gateway. So many cars are actually providing Wi-Fi within the car. The car is either connected to a cellular network outside, and that cellular network can be used for the vehicle-to-vehicle communication. It can be used for the vehicle-to-infrastructure communication. That's the method that software gets updated over the air. So that gateway provides a critical connection to the vehicle itself. And if you look at within that car then, and how those different systems are broken down, you can see that in this example here, all of the different systems, the comfort system, the infotainment system, the powertrain system, the ADAS system, they're all connected together by this common gateway. And this common gateway is, like I said, the connection to the outside world for software updates and for communication to other vehicles and other elements in the road. So looking at ADAS as a specific example, there's lots of different technology that's going into an ADAS system these days. Originally, the original ADAS systems were maybe just camera-based. Maybe there was just a backup camera, so if you were backing out of your driveway and someone happened to be behind you, it would notify you that that someone was there, so you could brake and stop. But today, these systems are becoming much more sophisticated in combining radar systems, or radar technology into the system, LiDAR, so basically using light, lasers, basically to be able to identify objects, whether or not it's daytime or nighttime, whether it's foggy or clear. So really to have a truly comprehensive ADAS system, all of these technologies need to play together because they all serve different purposes around the vehicle. And you can see here on this in this diagram kind of where typically you would use the different technologies, depending on what part of the vehicle you're addressing and trying to get driver assistance for. Digging a little bit deeper into LiDAR specifically, you can see that from the time that the signal is sampled, the original signal coming from whatever object out in the road is being directed toward the vehicle, to the low-level processing, the noise removal from that image, then filtering that image, and then basically adding or addressing the physical location using GPS or GNSS, and then the isolation, the location and localization and mapping, and then ultimately the object processing, determining what exactly that object is. So that chain of processing for this LiDAR example is pretty compute intensive. It's not a simple microcontroller is going to be able to handle that. It's going to require a pretty significant chunk of, in particular, DSP processing to manage that. And so if you look at that use model, you can kind of break it down into these four technologies that kind of come together to create the overall system that the vehicle will provide. So the imaging part still is very important. So having cameras, basically CMOS-based camera sensors that will visually detect if objects are there for the driver to identify. That's still an important part of the ADAS system. Then you have LiDAR that I talked about being kind of light-based. And then radar, again, is still that noise, echo bouncing off of the object itself is still an important part of the system as well. And that's broken down into short range and long range radar. So all of these types of technologies are all fed together to give kind of an overall picture of what's happening around the vehicle. And basically that all of those images and data values have to come together and be fused together. And that generally takes quite a bit of DSP processing to manage that. So looking at overall functional safety and how that applies to a system like that, you basically have different levels. They're called automotive safety integrity levels. And those levels can go from consumer-based or QM, where it's effectively the minimum amount of safety required to be built into the systems and ultimately the chips that build those systems, all the way up to ACEL D, which is basically the most safety critical systems have to comply to ACEL D. And basically where you fit in terms of which level of ACEL certification that is required really depends on how critical that application is to, for instance, maintaining or preserving life in an accident, or creating a system that will prevent an accident from happening in the first place. And what we see in the market is even applications that were, for instance, ACEL B, say mid-range level of certification and safety required in the past. So things like a radar system or a front view camera, maybe an aftermarket front view camera. Those are all migrating in the next generation or future generations of autonomous vehicles to be ACEL D, because these things are now no longer just user aids. They're actually becoming functions that are critical to the overall safety of the passengers in the vehicle, that all of these systems, the cameras, the powertrain, power steering, certainly all the safety related things like braking and airbags, those are all becoming ACEL D. The requirement is they must meet ACEL D certification levels. So what does that mean in terms of developing SoCs in particular, and then the SoCs that go into systems that are then placed or integrated into the vehicle? And when we look at that, if you look at the ISO 26262 standard in the industry for functional safety, there's really two major areas that need to be addressed by the system designers as well as the SoC designers. One is systematic faults, and the other is random faults. Now, systematic faults are really more about how the system is designed, the processes, the way that the SoC maker actually builds the SoC itself. So what processes are put in place to make sure that software bugs are not inadvertently placed into software that goes into the safety system? Are there design checklists for designing the hardware that is being built into the system? Are there other mechanisms like fault injection testing, things like that, that are sort of put in place to help with the systematic, the systematic building of an SoC and prevent user errors from making their way into the design? And then on the random side is actually the design itself. And the SoC example is trying to put mechanisms into the SoC itself to prevent random faults that can actually occur. So maybe there's a bit that gets flipped, and that bit can get flipped permanently to where that memory is compromised, or it can be transient type of faults where it could come and go. And that can be, for instance, if you have alpha particles that could potentially temporarily flip a bit in memory. So those are kind of the two different kinds of random faults that can occur. And so basically, in order to build systems that can prevent those, you really need to address both types of random faults and make sure that you're designing mechanisms into your SoC that are going to minimize the potential impact of those kinds of random faults. And so just to put a little color on kind of what is the definition of ACEL A, B, C, and D going up in terms of stringency and requirements, and really kind of it comes down to looking at what are the percentages of detection that must be met for single point faults as well as multi-point latent faults. And so you can see that from an ACEL B perspective, the single point fault metric is greater than 90%. So greater than 90% of all single point faults must be detected in a system in order for that system to be certified as ACEL B compliant. And as you move up to ACEL C and ACEL D, then those percentages become much higher. So in the ACEL D case, all 99% or more of the single point faults must be detected, and over 90% of the multi-point latent faults must be detected. And so systems need to prove that they can meet these standards in order to achieve third-party standardization and get sort of a stamp of certification. So in terms of architectures, what we see from Synopsys side in terms of the how safety is being addressed at the SoC level, traditionally, especially for SoC vendors that were moving into the automotive space, maybe they were new to the automotive space and they were just starting to build chips for it, is that they were relying pretty heavily on some of the traditional industry players. So some of the traditional industry microcontroller vendors have off-the-shelf controllers that other SoC makers would then integrate on a board. And so the SoC, the safety SoC, would effectively manage all the safety-related elements for that system, and the the actual SoC vendor themselves would have less to do as far as putting safety mechanisms in the chip itself. But as with almost any part of the semiconductor industry, in order to reduce power and area and all those sorts of things, more and more of the functions are being integrated onto the SoC, and this is true with safety as well. And what we're seeing is that in order to keep what's required for isolation between the functional aspects of an SoC and the safety-related aspects, is that many architectures are moving toward having a dedicated processor on board that manages all the safety escalations for the entire SoC. So there's kind of two ways to do it. You can allocate some of the processing resource of, say, the application. Say you have a multi-core application processor for an ADAS chip, as an example. You could allocate some of the processing capability of one of those processors to safety-related management tasks, but that obviously will have an impact on the overall performance of the device, plus that it could potentially compromise the isolation between the safety-related and the functional-related aspects of the device. And so having a small processor, and generally this doesn't require a huge high-performance processor, but a smaller processor that can basically be dedicated to managing the safety escalations on the device, is becoming a pretty common architecture that we're seeing in the market. So how does that look when you kind of bring that into an entire SoC? You can see there on the far left, and this is just a kind of an example device, say an ADAS device, with obviously the Synopsys spin on the peripherals and the processors there. But typically, regardless of whether it's a Synopsys-based IC or not, you see kind of this common architecture where the safety manager there and all the safety-related elements are highlighted in green. That safety manager itself is responsible for the overall safety bring-up of the device. It's basically responsible for running logic BIST and memory BIST in boot time. So as the product boots up, it needs to run those algorithms. And then as required for making sure that you have periodic tests, you will have windows where you will run all of those algorithms and run periodic tests, and that is all managed as well by the safety manager, the top-level safety manager. The other thing that the safety manager is responsible for is the error injection. So if you have safety mechanism testing where you want to simulate injection of errors into the system to basically test before you actually tape out a device, whether or not that those mechanisms will be there for real faults that may occur in the wild, that the safety manager is running that software as well. One of the architectural aspects that we certainly promote within Synopsys is having a separate dedicated safety bus. So to the point of trying to make sure that you keep isolation between the functional and the safety-related elements, having a dedicated bus in order to escalate real-time safety errors is actually very important. And so instead of having to wait for whatever delays might be in the system through the interconnect, through the peripherals themselves or whatnot, wherever that may occur, having a dedicated safety bus allows the fastest path to indicate a safety issue to the safety manager. Then the manager, based on what the priorities may be for different areas of the SoC, can make a determination of what needs to be done, whether the part needs to be reset or whatnot. Another aspect that's here that is important as far as Synopsys' product offering is the tie-in between the safety manager as well as the logic for memory BIST and logic BIST. So Synopsys has a set of products called Star Memory System and Star Hierarchical Systems that effectively create wrappers so that customers' IP, whether it's Synopsys IP or their own IP, basically can be tied into the same safe network, if you will, or safety architecture. And so in order to minimize the amount of extra work that a customer might have to do to basically get their existing IP, especially if it's IP that may come from, say, a consumer-based device, and they want to move that IP when they create a safety automotive device. They can still use that IP. They tie that off with the SMS or SHS logic, and then it can tie into the overall safety architecture. But independent of whether or not the architecture uses Synopsys IP, the concept of memory bits and logic bits being tied into a top-level safety manager is a very common architecture that we're seeing more and more in the market. So just some high level of why would a customer or an SoC implementation team want to integrate a functional safety manager. So as I said before, basically the idea is to have a ACEL D compliant dual-core lockstep processor that manages all the safety escalations. So it allows that you will have freedom from interference between the safety code and the application code. It provides a mechanism for independent and deterministic safety decision making. So basically, like I sort of alluded to, that you may have areas of the SoC that are more safety critical than others. And so you may decide that if there's a fault in a certain area of the device, say there's a subsystem that's managing a more critical safety related aspect of the device, then that escalation may warrant that the device has to be reset. But maybe there's another less safety critical area or subsystem within the SoC that maybe the safety escalation does not require a full. Maybe it can continue to run without having to reset the part. And so those decisions all can be made by the software, in the safety manager, and allow the integrator to make decisions on, what needs to be done from a safety-related aspect that's independent of what needs to be done functionally. The other thing that is an important aspect is the concept of software test libraries. So if you can reduce the overall overhead that software has to manage or deal with around safety, that's an important aspect of getting to market. And so you can isolate what's important from a software perspective on the application side from the software that's required for managing safety escalations and testing for safety-related issues on the device. And so that those software test libraries can actually be dedicated and run on the top-level safety manager. So I think one of the things that's important to note, and this especially goes to the concept of systematic safety, is that it's not simple enough to just say, okay, I've put a couple of blocks onto my SoC. They each are checkbox that they're ACEL B or ACEL D compliant, and so now I have a ACEL D compliant SoC. It's not that simple. It's a much more comprehensive type of requirements around a safety certification. So you really need to make sure as a vendor, if you're an SoC vendor and you're looking at IP providers, that you're asking the right questions about what exactly is being done for managing or for making sure that the certification that's done at the IP level, whether it's an interface peripheral or processor or anything, that how is that going to reduce what's required for the SoC to get to their level of certification? Because certification doesn't just happen at one level. It needs to happen for the IP, it needs to happen for the SoC, and then needs to happen for the module or the system. So everything sort of builds upon one another. And so it's really important to make sure that the IP provider is basically implementing a culture of safety, not just having some safety-related IP. This is an area that Synopsys has invested a lot over the last few years, and basically it's the idea that when we deliver IP to our customers, that everything that we're doing is helping to reduce the risk and basically accelerating the qualification for our customers' SoCs. We try to be consistent about the safety features, the development flows, and all the work products. There's dozens of work products that are generated by when you're building safety-related IP, and we're consistent about that across all of our IP portfolio. So the whole idea here is that we want to follow the letter and intent of ISO 26262, not to just basically check a box and say that we have some IP that's safety compliant or safety certified. We basically are sort of culturally building in safety to our whole flow. And it seems to be working because basically almost all of the top semi suppliers in the automotive industry are licensing our IP. So from a processor perspective, how does that look? And so just like with any of the IP that we've built at Synopsys, the processor side has been a very important part of that. And we're addressing it across the board. There's 4 major families of processors that we're targeting to have functional safety versions of, going from the EM family, which is our lowest power 3-stage pipeline processor family, really targeting kind of the more of the controller types of applications for standalone. So if you have a standalone safety microcontroller and that's doing things like keyless entry or basic sensors, then the EM22FS that we've just launched over the last couple of months is addressing that. As their performance requirements go up for things like vehicle-to-vehicle networking, automotive storage, or electric vehicle battery charging, then our HS processor family, that's a 10-stage pipeline processor, is probably more appropriate from a processing perspective, and we have functional safety versions of that as well. We have our dedicated vector DSP processors called VPX, and then we have our embedded vision engines as well that are combining vector DSP with a scalar core, as well as having convolutional neural network attached to address, some of the, especially in the ADAS space, some of the applications required there. Again, all of the safety features are pretty common, and I'll show a slide here next that kind of walks through a few of them. But basically, we're trying to make sure that the lockstep capability, ECC protection, and how we go about designing and developing that IP is consistent across the board. We also have compliant tools, so that's an important aspect as well. As you simply can't put some hardware out there and say, okay, it's certified and it's going to meet your needs. Basically, you have to have a tool chain that's also ISO 26262 compliant, and our MetaWare development toolkit for safety around all of our processors meets those needs. So this is just a snapshot of kind of some of the safety features that are important across the board, and you can kind of see from EM, HS, and EV cases here, things like ECC on the memories, basically providing protection on key registers, having a safety monitor for dual core lockstep, making sure that if you require ACEL D, and generally that requires having a dual core lockstep mechanism where identical code is being run on both cores, and they're being checked every cycle between one another to make sure that there's no glitching or no faults injected there. Diagnostic error injection, having watchdog timer, a windowed watchdog timer, basically protection on the buses, and then being able to enable things like memory bits and logic bits that I talked about. And then the safety documentation is another important part of that. All of the reports that are required for certification are an important part of what we do in our processor development, and we provide that to our customers to basically facilitate their own certification efforts at the SoC level. So going back to that diagram, the use model where we're combining imaging, short and long-term short and long-range radar as well as LiDAR together in a sensor fusion application that's used for an ADAS development. You can see kind of we have products that I mentioned here, the functional safety versions that will address different aspects of the ADAS system. So on the sensor side, depending on the level and the number of sensors required, you may need something like our embedded vision processor and the vector DSP capability there, and the convolutional neural network that's used for surveillance and image detection and recognition. On the LiDAR side, it's something similar where that higher level of processing capability is required. On the long-range radar, having FFTs combined with the DSP capability that's built into our 10-stage scalar processor is probably sufficient for the DSP requirements in that space. And then for the other part of the radar that feeds into the overall system, we have our dedicated 256-bit wide vector DSP engine that can efficiently process that data. And then it may or may not be required that you have yet an additional DSP that is sort of processing all of that data coming together to basically provide a single look to the application processor for everything on that that's part of the ADAS system. So kind of stepping back at a high level, how does that kind of look? So the idea is that, again, the functional data flow and the safety data flow are all separated. And so whether that's, the functional flow is feeding from the sensors themselves, basically through the interfaces to the memory, being processed, whether that's with our embedded vision engine, our dedicated vector processing engine, or a simple scalar processor with DSP capability, that all of that path can be managed by different aspects of Synopsys IP, certainly, and goes into the overall system. And at the bottom there, you see that it's also critical to keep the safety-related elements separate, and that's where something like an EM-based safety manager combined with our star memory system or star hierarchical system will basically provide the overall safety architecture to separate the safety flow from the functional data flow. So another aspect that's critical, and this kind of moves toward, or it's part and parcel with the systematic certification, is to make sure that the flows themselves for developing an SoC are basically adapting to the ISO 26262 standard. And so if you look kind of at a typical flow on the design side, where you're moving from the instruction set architecture to the specification to the digital SoC specification, and then off to the RTL design and implementation, that's a flow that's common in any device. And then on the verification side, you have a similar flow where you have module design, sort of bottoms up verification flow, module design to processor level to validation, and then to the basically testing, whether that's in an FPGA design or in the final ASIC. The safety related elements need to go hand in hand with that development effort. And so as you're developing, you can't add safety sort of later. You have to look at it from the beginning and from the architectural beginning of the device. And so as you're defining the architecture, you need to basically be looking at your safety plan. You need to make sure that the hardware safety requirements are being implemented or integrated into the SoC itself. You have to look at the overall goals, and then start looking at the fit rate analysis and what ultimately are going to be the set of hardware features that are required. You want to make sure that whatever hardware features you're putting in are going to enable your device to meet the minimum requirements, whether it's an ACEL B at 90% or ACEL D at 99% fault coverage. You're going to have to basically make sure that the hardware mechanisms are put in place there. And then on the verification side, you have a similar hand-in-hand kind of relationship where you want to basically check the coverage, and you want to do that simulation effectively before you tape out. And so you want to have this fault injection mechanism, or fault injection campaign, as we call it. Then you generate the FMEDA report, and then that feeds into your overall safety manual. And so this is a process flow. This example here that I'm showing is the one that we use when developing our processors. A very similar flow would need to apply at the SoC level for any vendor that wants to basically play in the automotive space. And so we promote, that when we do this and the safety-related documentation that comes out of our own flows and building our processors is something that our customers can directly leverage. So if we're doing a lot of the work and the work products that we generate for this, and this can be multi-man years of effort, just to put it in perspective, we leverage that and we give that to our customers, and so our customers then can reduce the overall effort that they have to then do when they're developing and certifying their own SoCs. So how does that sum up? So basically, the idea here, and one of the things that we promote when Synopsys is that, we're not just providing one little piece of the overall safety solution. We actually are providing aspects of all of it. So whether it's interface IP, whether it's processors, whether it's the functional safety test network or infrastructure, all of those things are part of the offering in our IP portfolio. But we've taken that a little bit further even, and we've actually started to integrate a lot of these things together. So we have several customers that have licensed multiple portions of our overall safety portfolio. And as an example, we've worked with our SMS SHS team to basically build systems that the memory BIS, the logic BIS, the firmware that drives the algorithms for those BIS elements is part of and runs on our ARC processors as well. And we've gone off and we've validated that with several customers as well as through several demo kits. And so the idea is that from a Synopsys perspective, we can basically help provide to customers a complete FUSA solution for safety critical SoCs. So from the processor all the way out to the memory and logic BIS and the safety certified IP as well. We have a set of expertise in-house as well. So basically, we can certainly help with our customers' configuration of their SoC. We can actually take it a step further, even if we need to do more work in helping certify the customer's SoC, maybe even facilitating some of the work that they have to do with some of their own in-house IP as well. So the idea is that we're reducing our overall customers' risk in getting to market quicker and basically building more reliable and safe SoCs. And this is, in particular, we're seeing this is pretty important for the market as it goes forward, because the automotive market is predicted to have quite a bit of growth. There are a lot of new players into the market. So you have your traditional players that have been in the industry for decades. They don't need this kind of help, right? They've been doing this forever. But in a lot of emerging markets, a lot of new semiconductor vendors are coming up that want to get into the automotive space. They don't necessarily have the depth of experience that some of the traditional vendors have. And so they rely a lot on IP providers like Synopsys to be able to come in and help them get to where they need to go in a reasonable time. Okay, so that was all I had. I guess we open it up to questions. Okay. First question, many IP providers claim ACEL certified. Are there differences in how is what you are doing better? That's a good point. There are, it isn't just a one-stop shop. Okay, I have ACEL certified. There's, I talked about the differences between ACEL levels from QM all the way up to ACEL D, but it's important for SoC vendors to ask their IP providers on what are they doing. So basically, what work products are going to be generated and then look at their safety flows as well. Do they have an independent safety council, if you will? Do they have safety managers who are that are isolated from the design itself to make sure that they're doing checks on how the process works, how the flows are put in place, how the IP is being designed before it gets developed, so that when the IP is provided, it's providing the most robust piece of IP that an SoC vendor can license. And I think that Synopsys does an excellent job of that. We've spent a lot of time and effort on that over the last, say, 8-10 years, and I think we've gotten to a point where we have a pretty good feel for it, and I think some of the other vendors, may claim that, but I'm not sure they're in the same league there. Okay, next question. You were talking about systematic and random faults. How is Synopsys addressing both cases? So I sort of was talking about that on answering that last question, that we have spent a lot of time putting together an independent team within the IP organization of Synopsys to manage all of the safety-related flows. So they're the ones who sort of have to approve everything that we develop in terms of the flows for any piece of IP, whether that's a processor, whether that's a USB controller, whether that's a PHY, anything that's going to be safety certified. That independent body or group inside Synopsys is going to manage that. They're also our liaison to third parties. So we work with third-party vendors like SGS2 to independently certify our process flows as well as our IP itself. And I think that's pretty unique for IP providers. Okay, next question. The automotive semiconductor market is traditionally dominated by a few key players. What does Synopsys provide that allows semiconductor vendors new to the market to be successful building automotive SoCs? So that's largely what I tried to address there at the end, where there were several vendors that have kind of dominated the safety-related IC market over the last, say, 25, 30 years. But because the market and more ICs are going into these devices, a lot more semiconductor vendors are coming into the space. And so they may or may not have that level of expertise required for, building these certified SoCs. And we pride ourselves on being able to help those vendors get where they need to go, right? As I mentioned, over the course of the presentation, the flows that we put in place to guarantee the systematic, or to minimize the possibility for flows based on systematic design-related errors, as well as the effort and the work products that we generate for our IP itself to guarantee that the IP is going to reach that certain level of ACEL requirement. Okay, next question. Do you see any of the technologies you talked about for ADAS, LiDAR, radar, vision becoming dominant? I don't think that any one of those technologies will actually be, it's not a race to see which one becomes the dominant one. I think they're all complementary, and that's kind of what I showed in that diagram at the beginning with the car and all the different technologies kind of around it. There are certain aspects that, for instance, having the camera and image object recognition is the best for detecting somebody basically in the rear view of your car when you're backing up. But when you're driving down the road and you have and it's a foggy or dark unlit road, then a technology like LiDAR or in some cases radar is a better type of technology for detecting objects that may come into the road or other vehicles or other things that may be in the way that you want to see well in advance to make a decision on what needs to be done. So I don't see that one dominating over the other. I see them continuing to complement each other. And again, to be able to integrate and incorporate all of those technologies, then basically the processing capability that's required for those is pretty high. Okay. Will the safety certification requirements get more stringent for level 4 and level 5 autonomous vehicles? Yeah, absolutely. So as I showed in one of the slides, where even just the mechanisms inside existing cars going from sort of today or the previous generation moving toward current generation and the next generation, before we even get to any fully autonomous vehicles, the certification requirements are going up because more of the systems are automated, and they all have impact on basically people's lives in those cars. Then the certification requirements are much higher. So anything that has to do with impacting human life is going to be at the highest level of certification. And certainly as you get toward fully autonomous cars, then it's going to have to be, the highest level for pretty much every system in the vehicle. is safety certification required for infotainment? If so, why? I think that what we're seeing is today, anyway, that the infotainment is ACEL B as in boy, so it's not quite as the level of safety certification for other, more critical systems. But what we're seeing is that because some of the architectures are common across multiple platforms within the device, if they want to reuse a certain platform in an infotainment system and largely use some of that IP or those subsystems or SoCs in other areas of the device, then they need to make sure that they can get to that level of certification, the highest level, ACEL D. All right. Is ISO 26262 a worldwide standard, or are there other standards for functional safety around the world? There are other functional safety standards, but mostly a lot of those are around, say, factory automation, so IEC standards for, medical or factory automation, things like that. But in terms of automotive, pretty much ISO 26262 is the standard across the world that all the automotive vendors are compliant to. There's a question about LiDAR data. Computing power requirement for localization and perception using LiDAR data. What can be common? What has to be different? If I understand the question correctly, I think there's a certain set of DSP requirements that are pretty well understood, and I think those can be common. There may be other hardware accelerators that may assist and boost the performance in that space, and so those hardware accelerators may be unique to each vendor. But I think there is at least a common set of DSP processing algorithms that are pretty much common across the board, and so it's just a matter of building in the DSP capabilities that will meet the performance requirements, and then obviously in any type of SoC, that building it with the least power and area is going to be an important aspect. All right. Is it more expensive in terms of silicon area to support ACEL D versus ACEL B? Generally, it is because ACEL D generally requires dual core lockstep capability. So, for instance, in a small processor like EM, the easiest thing to do is to basically duplicate the core and have both cores running, the same code and lockstepping it. But what we've seen is even in that scenario, because memory dominates and you're using shared memory dominates the overall area and power, that the overall impact of adding that second core is fairly minimal. On a much bigger processor core like our embedded vision processors, we didn't want to just go and to get from ACEL B to ACEL D, just basically duplicate everything, because that's a fairly large, big compute engine. And so we've put mechanisms inside the core for creating visibility, duplicating in some areas where it's required, but basically putting other error detecting codes and other mechanisms inside the device itself or the processor itself to be able to get to ACEL D without having to fully duplicate everything. But I think in general, an ACEL D level chip will have more hardware than an ACEL B. All right. If I implement a functional safety manager, do I need to implement ACEL support in other processors on my device? I think the answer is generally yes, because you have to look at the overall device. So you can't just say, okay, because I have ACEL D certified safety manager, I don't have to do anything else in the device. You have to holistically look at the entire device. The entire device has to be meet the default requirements for ACEL B or ACEL D. And so basically that's what each SoC vendor needs to go back and look at, is how do I get to where I need to go? Generally, that will require safety mechanisms on many of the aspects of the SoC. What do I need to do to get? So the next question is, what do I need to do to get my device as ISO 26262 certified? So it's a fairly involved process. Generally, you will need to show to a third-party house, and in our case, we use SGS2 to basically validate both the systematic flows for developing the SoC, as well as basically going through the process of certifying the actual SoC. When those SoCs are sold to the module vendors, you can guarantee that the module vendors are going to audit and basically make sure that they go back and check with their SoC provider on what level of certification, and they're going to go through and comb through all of their processes, all of their safety documentation, FMEDA reports, DFMA reports, all the things that are part of the overall safety deliverables, and that will all have to be done. And so generally, it's a several-year process to get from where you start designing something to where you're actually certified. So it's pretty involved. All right, let's see. Is ISO certification being used for applications other than automotive? I'm not sure if that's true or not. I know there's, like I said, there's sort of sister standards, if you will, SIL levels for factory automation. But I think ISO 26262 is largely standardized for automotive. But there is a lot of work within the standards body to talk to or to work with. So, for instance, security standards to sort of align on safety and security. But I think largely it's pretty much dedicated to automotive. There's a question, is there other standards of safety? If there are, why are you using ISO 26262? So like I said, there are other standards for safety related around other industries. So there's ones that are dedicated toward factory automation, ones that are dedicated toward medical. And largely there's a lot of overlap on what's actually required from a hardware and software perspective. But predominantly for automotive, ISO 26262 is the standard that the industry is rallied around, and so that's why we're focused on our automotive-related IP around that standard. Okay, what safety reports and documentation do you provide with your functional safety processor? So there's a whole slew of documents that we provide as part of our basic safety package, and generally there's a whole list of other documents that we can provide as well that aren't part of the sort of off-the-shelf, if you will, safety documentation package. Basically the certification, the certificate itself, FMEDA reports, DFMA reports, safety manual, those are all off-the-shelf part of the deliverable from our IP. But some other things like, if a customer wants to validate or verify our verification reports, some of our other documentation, then we can make those available to customers as well. It's really, we like to engage with each customer individually to understand what their needs are. Okay, let's see. If a vendor says that IP is safety compliant, do we still have to verify that? And if we do, then how? So I think that I would ask those questions that I brought up earlier. They may say it's safety compliant, but I would ask, is it system, are there flows in place for systematic compliance, or is the IP, what are the work products that you're generating, and start asking some of the questions. What exactly is the IP provider going to give to you to help you with your SoC certification? It's not just a checkbox that says that they validated one piece of software, say, that it needs to be a much more comprehensive solution. And I think in general, I would recommend that the SoC vendor even audit the IP vendor and get access to exactly what is the set of work products that are going to be generated for their IP. Okay, do you suggest anything for newcomers in the semiconductor industries which are trying to enter into automotive SoCs? I think it's largely just a learning curve, and that's why we've done several workshops around our IP. We generally will go, for instance, in China, we'll go visit several customers and do workshops where any of the semiconductor companies that are new to the market that want to get in can come and listen to our safety experts talk in a little bit more depth about what it is that we do, what it is that we provide, how are we going about developing our SoCs to sort of guarantee that the level of ACEL certification that we're claiming on the IP itself. So I think that's probably a good starting point, is to come to those workshops, and then certainly, you know, we can provide yet a higher level of safety consultation if that's then required. Okay, how can we recognize the random faults? How much those SoCs are robust to detect them? Basically, there's two levels, right? So there's a fault injection testing that you do when you're developing the SoC, so that you can effectively create a simulation of faults, so that you make sure that the hardware mechanisms are detecting that. Once you're in sort of mission mode, if you will, then you're going to then use the mechanisms on the IP or the overall SoC to then detect that. So for instance, in a dual core lockstep mechanism, that's the whole reason that you do that, right? You're running the code on 2 cores with a, say, 2 to 4 cycle delay between the instructions running on each of those cores, so that if something were to glitch and you were to detect that it didn't, you know, the instruction didn't execute exactly the same on both cores, then you flag that as a potential fault case. Okay. So the question is, how does the Synopsys processor, which our functional data flow is not compromised by the safety manager? How is dependency taken care of? If I understand the correctly, so this is the question that I answered earlier. You will still need safety mechanisms in the functional processors themselves. When you say data flow compromised, I assume that the concern is that somehow the safety manager is going to inject something into the data flow, and I think generally the idea is that the dedicated safety manager is isolated from the sort of application flow itself. And so if you only run the safety code on the safety manager, then you don't need to necessarily worry about that safety code running on, you know, another application core. And so in general, other than, you know, latency that might be tied to the functional aspects of the safety manager to the rest of the system, there's effectively no bearing on it. It shouldn't have any impact. There shouldn't be any data dependencies or anything like that that could compromise the actual normal application. Okay, let's see, I don't know how many more questions we have. We probably have a couple more minutes here. How will automotive SoCs ensure the safety of the consumer on possible conflicts? Is there any default safe mode that should the device be certified? So that's part of the overall process that the SoC vendor has to go through. So basically, the device itself has to show basically everything that's supported on that device. So yes, you will have to show how basically that device is going to deal with virtually any safety-related issue that may come up, and make sure that it can handle it. And that will be part of what the module maker or the end user, or you know, the OEM is going to demand from the SoC vendor. Is ISO 26262 applicable on software layers too? Yes. So there is a if you look at the overall, they call it a V diagram in the ISO 26262 standard, there's software-related and hardware-related elements to it. So the software also has to be certified, and that's why it's important that So for instance, we have our own development tools. The development tools also have to be certified. And so basically everything that's involved in that system has to have a level of certification. What is error injection? I observed a few times in the webinar. Yeah, so error injection is basically having a set of tools. You can think of it as almost like simulation, right? So error injection is basically having a mechanism to basically inject errors into the system and make sure that the hardware features that are put in to detect those mechanisms are working correctly. And you want to do that before you tape it out, so that when these types of faults potentially occur in the field in real time, that you will catch them. Okay, let's see. Yeah, one more question was about the webinar. I do believe that it will be, it is recorded and it should be available online sometime soon.
All right.
Okay.
Well, thank you so much, Rich, and thank you for all of you for joining today's webinar. This does conclude our presentation. Thanks, Rich.
Thank you.